To review over section 11.4, we're going to talk about the heights of students. We can see that guys and gals are both having their heights listed as a normal curve. So remember, the mean on a normal curve always goes here in the middle, okay? And we also have both of them on separate scales because generally males tend to be a little bit taller. So when they ask, what is the percent of the population between 63 and 68 inches for women, we would look here on the 63 and the 68. And we know from our empirical rule that 68% of the data lie between the first standard deviations. So this is one standard deviation to the right and one standard deviation to the left. So 68% of your data lies between there. For question 2, what percent lie between 65.8 and 68.5? For this one, we're going to go back over to the male side, and we look at 65.8 here and 68.5. Now, it's important to note that this middle one's on the mean. We know this is in the middle, but this one to the left is on the first standard deviation. We're going to use that 68 then again, because 68 goes from one standard deviation to the right and to the left. It includes that many males that are between 65.8 inches and 71.2. But we only want to go to the 68.5, so that would be half of it, and we would have 34% for our answer to number 2. The percent between 63.1 and 73.9. So here's my 63.1 and my 73.9. Note that those are both 2 standard deviations from the mean. So from here to here, we would have our second number that we memorize. Remember, 95% are between 2 standard deviations. That means 95% of the males would measure from 63.1 inches to 73.9 inches. We wanted to know what heights the women might be if there's 95% of them included. Remember, 95 goes with that second standard deviation. So we're going to go out 2 standard deviations to the right and the left. And then we'd have 60.5 and 70.5 as our answers for the heights that the women would be between. And then finally, what percent is below 60.5 for the women? So if I go look at the 60.5, here we are. Note that that's at the second standard deviation below the mean. We want to know what percent are below right over here. First, we need to remember that from the second standard deviation, both positive and negative, we have 95% of our data. Well, the whole curve represents 100%. If we take 100 minus 95, we get 5%. That's our really, really tall and really, really short females. We're going to divide that into 2, so we get just this left side here, and that would be 2.5%. So remember that you should know the 68, the 95, and the third standard deviation that we didn't talk much about here is 99.7. Know those 3 values for your first, second, and third standard deviations. Now, when it comes to talking about actual data, here we have Marco. So if we look at the guys, we've got 1 standard deviation above for part A. Well, if he's 1 standard deviation above, that means he's right here. He is 71.2 inches tall. If he's 2 standard deviations above the mean, we'd want to look to the right again, so we'd go over here to 73.9. That's how tall he would be. But now he's actually 1.5 standard deviations above the mean. Now there's a few ways you can do this, but let's think of it this way. If you had each standard deviation, each space between each of these lines, if you will, is 2.7. Every increment on this bell curve for the gentleman is 2.7 inches. We have 2.7 standard deviations for each grouping. We want one group of 2.7 plus a partial of another. We want the half. We're going to take that times 1.5. When we get 4.05 by multiplying his 1.5 standard deviations times what each standard deviation is worth of 2.7, we want to add that to the mean of 68.5 because that was from average. So that would give us 72.55. That's how many inches he would be tall. We can do the same thing now with this formula when we know he's 1.2 standard deviations. We want each standard deviation is worth 2.7 inches. We want 1.2 of those, which gives us 3.24 inches. We will add that to our mean of 68.5, and that gives us Marco at a height of 71.74 inches tall. One more example. We have Sarah now, so we're going to look at the gal's curve. She's 1.7 standard deviations above the mean. That means she's this out one and some more. So she's about right here, but we want to know exactly how tall she is. Each of these standard deviations is worth 2.5 for the females up here. So we're going to take a 2.5 standard deviation, that's what each chunk or bar is worth, if you will, times she is 1.7 of them. So she is 4.25 inches above the mean. That means we need to add on the mean, and she will be 69.75 inches tall. So each time we did this, we took the standard deviation of our curve in general, like 2.5 or 2.7, times their standard deviation. We're going to refer to this number, their 1.7, we're calling that her z-score. Z-score is basically how many standard deviations a certain data point is away from the mean. Then we would always add on the mean, and remember, mean has a symbol of mu. That will give us x. X stands for like the actual height. So this is one formula you could look at to find an actual data piece if you know the standard deviation of the person and in general plus the mean. Now oftentimes we know how tall we are, but we don't relate to standard deviation. So Lola here, she's 68 inches tall. We can tell she's 1 standard deviation above the mean. It's easy when they're on one of the actual markings. But if Renee was 62 inches, we want to figure out how many standard deviations she is. We know she's going to be shorter, so she's around over here. We know she's at least -1 standard deviations, but definitely not 2. In order to do this, we're going to find out how far off the mean she is in general. So we're going to take her 62 inches and subtract the average height for women, so 65.5. So that will give me a -3.5. Now that tells me that there's 3.5 inches here between the average and her height. Remember, each chunk or section, if you will, is 2.5 inches. So this is 2.5. That's what we call a standard deviation. We know she's 1 and a little more. We want to divide her 3.5 inches below the mean by the standard deviation, what each of those little bars is worth. And if we do that, we get -1.4. This is her standard deviation. Now remember from the last slide, we call this her z-score. This is how many standard deviations from the mean that Renee is. Here we have Marina. She is 68 inches tall. And so if we went over to Marina, we know she is 1 standard deviation off the mean. Okay, so we'd say her z-score equals 1, and that's nice because we don't have to do any calculating. For Steve, he's 71 inches tall. That would put him right here, a little bit before. Notice how he's something less than 1 standard deviation. So who's more relatively tall for their gender? Definitely Marina, because she reaches the first standard deviation. For Steve, just to verify, for Steve, I took his height and subtracted the average and found he was just off the mean and divided it into 2.7 inches because remember, that's what every one of these little bars is worth. And he is 0.93. That's his z-score. He is not quite as far from the mean as Marina is, so she would be taller for her gender. Now, one last concept. We like to know your percentile. So, for example, if Alexis is 50% taller than the women, now we have Alexis here. Alexis is said to be 3 standard deviations above the mean, so that puts her right here. She is taller than a ton of people back here, but we want to know exactly how much. So in order to do that, we'd actually have to use something that we can do on Desmos. Okay, we can estimate that with those 6895 numbers, but we're going to just use Desmos. And in order to do that, you're going to go to Desmos and click on the Functions tab. Okay, so here we see the functions circled. And then you would click on Normal, or the Distribution and Normal Distribution. It's going to give you a screen like this one. You will type in, or make sure you click this little check. It says Find Cumulative Property. This is the number you're going to fill in most commonly, the max. So for the last page, she was 3 standard deviations above the mean. I would type that, and it's going to tell me how many people she is taller than, what percent. So here you'll see I did type in the 3, and it says 0.998. That means Alexis, being 70 or 3 standard deviations tall, 70.5 inches tall, she is taller than 99.9% of the population. She's quite tall. You could do the same thing here. I have Marvin. Remember in the beginning, Marvin is 2.1 standard deviation. That means he was like right here. All you have to do, though, you don't have to figure out how tall he is. Yes, I give you that, but we care about his z-score, his standard deviation. I type in my 2.1 on Desmos. It tells me he is taller than 98% of the males his age. Here's another one. I've got let's see, there we go. I've got Miguel, who's 74 inches tall. I had to figure out his z-score. And one thing we should verify, if you know someone's actual data, call that X, and you subtract the mean, the average of the males, and divide by the standard deviation, you will get their z-score. So this is the formula you will want to calculate someone's z-score. That's what we did here for Miguel and Jackie. Miguel, being on the males scale, we found his z-score to be 2.04. He is taller than 97.9% of the people. As opposed to Jackie, who she has a negative 1.4. Now we know she's shorter, but she's not quite as extremely short as he is tall. She is taller than just 8% of people. You'll always need that z-score in order to find the percentile. The percentile is the percent of people or data below your z-score.